All right, let's talk about matter. It's literally everything. I mean, the device you're watching this on, the chair you're sitting in, even the air you're breathing right now. It's all matter. And it exists in these states that are so incredibly common, we just take them for granted. But when you really stop and think about them, they are fascinating. So let me ask you a question. What could a solid book, a glass of water, and the air you're breathing possibly have in common? I mean, they couldn't seem more different, right? But the answer is, they're all matter, just showing up in its three most familiar states. And getting a handle on these is really the key to understanding the world around us. So let's start with what seems like the most straightforward one, the solid. It's rigid, it's stable, it's totally predictable. Or is it? Yeah, as we're about to find out, solids can be surprisingly tricky. So on paper, solids look pretty simple. You think of something like a pen or a block of wood, and yeah, it's got a definite shape, a fixed volume, and you can't really squish it. It's rigid. Easy enough, right? Well, let's poke a few holes in that idea. Okay, what about a rubber band? You can stretch it, you can bend it, you can completely change its shape. That doesn't feel very rigid at all. So what gives? Is a rubber band not actually a solid? So here's the deal. A rubber band is absolutely 100% a solid. See, the important thing isn't that its shape can't change, it's that it regains its shape when you let it go. That tendency to snap right back is the key. And hey, if you pull too hard, it breaks. Another classic solid move. All right, puzzle number 2 for you. Let's think about salt or sugar. You can pour them, right? And they take the shape of whatever jar or bowl you put them in, which sounds an awful lot like a liquid. So are they solids or not? The trick here is all about perspective. You have to stop looking at the whole pile and zoom in on a single tiny crystal. Each individual grain of sugar has its own fixed shape, its own fixed volume. It's a perfect little solid. You're just seeing what happens when you get millions of them together. And now for a last solid state head scratcher, the sponge. We just said that solids have, negligible compressibility. You can't really squish them. And yet, we can all squeeze a sponge into a little ball. That seems like a total contradiction. So what is going on here? The secret is in what you can't see. A sponge is just full of tiny little holes, and those holes are filled with air. So when you squeeze a sponge, you're not actually compressing the solid material at all. You're just pushing all the air out of those little pockets. The solid itself is just fine. Okay, so we've tackled the tricky nature of solids. Now let's see what happens when we dial up the energy a little bit. We get our next state, the liquid. And the thing that defines a liquid is its ability to flow, which is a huge change from those rigid solids we were just looking at. So this is really the key difference. A liquid has no fixed shape of its own. It'll just take the shape of whatever container you pour it into. But look at what they do have in common, a fixed volume. 50 milliliters of water is always going to be 50 milliliters of water, whether it's in a tall, skinny glass or a wide, flat bowl. Now, this amazing ability to flow gives liquids a special scientific category. They're known as fluids. It's a pretty simple definition. Basically, if it's not rigid and it can flow, it's a fluid. And that idea is what really separates them from solids. But here's where liquids get even more interesting. They're not just these self-contained things. Other states of matter can actually mix right into them. For example, gases from our atmosphere, like oxygen, can actually diffuse and dissolve directly into water. And this isn't just some neat science fact. It's absolutely essential for life on Earth. It's the entire reason fish can breathe. The oxygen they need to live is literally dissolved in the water all around them. All living things need oxygen, and for everything that lives underwater, this process makes it all possible. Okay, from the solid to the flowing liquid, let's crank the energy up even more. Now we get to our third state, the unseen, super energetic gas. Gases are everywhere, but since we can't see them, we have to understand them by the powerful effects they have on everything else. To really get the most dramatic property of gases, just imagine trying to squish each state in a syringe. If you put chalk in there, a solid, that piston is not moving. With water, a liquid, maybe it moves a tiny, tiny bit. But with air, a gas, whoosh, the piston moves super easily. This high compressibility is exactly why we can cram a huge amount of gas into a small tank, like for a barbecue grill. And what about speed? Think about how the smell of cooking food can fill an entire house in just seconds. Well, that's gas in action. The tiny, high-energy aroma particles fly off the food, mix with the air, and just explode outwards, spreading super fast to reach you, even if you're in a completely different room. That tells you that gas particles are moving with some serious speed. So, we've seen all these different properties, right? Solids are rigid, liquids flow, gases just expand everywhere. But why? Why are they so different? Well, the answer to everything we've just looked at comes down to one single, fundamental idea. It's all about the energy of their particles. Okay, so in a solid, the particles have pretty low energy. They're locked into this tight, organized pattern. I want you to imagine a dance floor that is so jam-packed with people that nobody can actually move. All you can do is just kind of vibrate in place. That is a solid. And that locked structure is what gives it a definite shape. Now, let's give those dancers a little more energy and a bit more room to move. In a liquid, the particles are still pretty close together, but now they have enough energy to slide past one another. They can move, they can flow. And this is why a liquid can take the shape of its container, but still has a fixed volume. And then you have gases. We're talking maximum energy. The particles here are like a bunch of super bouncy balls that have been let loose in an empty gym. They're really far apart, they're zipping around randomly at crazy speeds, and they will expand to fill any container you put them in. And that huge space between them, that's exactly why they're so easy to compress. And this is where it all clicks. Just look at this table. The particle behavior at the top, how they're spaced out and how they move, that dictates everything else below it. The rigid shape of a solid, the flowing nature of a liquid, the compressibility of a gas. It all comes back to the energy of their tiny little particles. It's really that simple and that beautiful. So we've seen it's all about energy, right? A solid has low energy, a liquid has a bit more, and a gas has a ton. And that leaves us with one last really fascinating question. What happens if you take a gas and you just keep pumping in more and more energy? What new state of matter comes next?